Next is what? The second one. At a point on equatorial line, that is electric field of an electric dipole at a point on each equatorial line. Consider an electric dipole consisting of 2 point charges minus q and plus q separated by twice L. Let P be the point of observation where we want to find electric field E. Okay, and let this P point of observation be at a distance r from the middle point of an electric dipole. Now for this to find out electric field E at this point P, you need to join AP and BP as shown in the figure. Okay, now when you think of electric field E due to this negative charge minus Q at A, to find out electric field at P, then your electric field P at this point P, we have to assume that there is a test charge here. Okay, so due to this negative charge, electric field will be pointing toward PA, and due to this positive charge plus small q at this point P, electric field will be along this BP, or you can say PD, because this is a positive charge, so it will be acting outward. Negative charge, it will be acting toward the negative charge. Now what happened? Just to find out this distance AP, because we will require to find out that negative, for negative charge, what happened? It will be what? Your electric field E negative, like this. It will be equal to what? 1 by 4 pi epsilon naught 4 pi epsilon naught into magnitude of the charge is how much? Q, and we require the distance square from here to here, AP square. So how to find this distance AP square first? Now you will see a triangle here, right triangle AOP, right? AOP. Now what happened? As this is a right triangle, and in this right triangle AP is the hypotenuse. We know that from Pythagoras theorem that AP square is equal to AO square plus OP square. Got it? So instead of writing AP square, we can write as what? AO square plus OP square. That is what? AO is what? L. OP is what? R. So it will be what? R square plus what? L square, like this. Got it? So let's see. So what happened here? We see that electric field E, yes, this one, right? So your electric field E plus first E minus, let's do it for E minus as I have done for E minus will be equal to what? 1 by 4 pi epsilon naught Q divided by AP square, right? It is equal to what? This 1 by 4 pi epsilon naught into Q divided by R square plus L square, and it will be acting along what? PC, or you can call it as PA. Now for E plus, similarly with that, E plus will be acting along this 1 by 4 pi epsilon naught q divided by bp square, distance square. So your bp square will be again same thing, Pythagoras square, r square plus l square, because this angle is theta. Got it? And this is just like an isosceles triangle. Got it? Isosceles triangle APB. AP will be equal to BP, right? So what happened? AP and BP being equal, they are isosceles triangle. So AP, when you take it triangle, right triangle here, also AP will be equal to what? This triangle BP, right? So same thing, it will be coming here in this r square plus l square here also. Got it? Now since angle angle PAB is theta and is also equal to angle P what APR, because this angle as this and this are parallel. Got it? These two are actually of the same magnitude, E minus here and E plus here. E minus, let me zoom in. Okay, so your E minus here acting along this PC, E plus acting along this PD. These two are of same magnitude, 1 by 4 pi epsilon naught q divided by r square plus l square, both are like that, so equal in magnitude. So when you try to do this, what your triangle law, parallelogram law or vector addition, or triangle law vector addition, you can say both, but it will be better to say parallelogram law or vector addition here, because here both are same. Got it? And moreover, this is just starting from the same point. So what happened? To equal what adjacent vectors, okay, of a parallelogram, naturally its resultant will be acting along its diagonal. So when you try to complete the parallelogram, what happened? The resultant vector of this E minus vector and E plus vector will be along this diagonal, and this diagonal will be parallel to this axial line of the electric dipole. So what happened? This, if this angle is theta, this angle must be also theta, what we call as alternate angles. Similar to this also, this theta also, this angle will be equal to this angle theta, because this is a corresponding angle, right? So what happened? To find out electric field due to this E minus and E plus, what happened? When you resolve it, this E plus into two rectangular components, one along PR, another along PF, then you can also resolve similarly E minus vector along this PC, okay, into two rectangular components, one along PR, another along PE. So what happened? Your component of this E plus along this PF, component of E minus along this PE will cancel each other, and that remains is what? This horizontal component of E minus and horizontal component of E plus. So what happened? For E plus here, it will be, this component will be E E cosine of theta, cos of theta. Got it? For this one, I mean E plus. For this E minus, again it will be again having one similar E cosine of theta. Got it? Like this. So that for E plus and E minus being in equivalent magnitude, so let me not mark as E plus and E minus here. Instead, E cos theta for this one. So E sine theta for this component along this PF, E sine theta along this PE for this E minus component. So that two will neutralize each other. So these will only remain. So your resultant electric field E will be what? E plus E cos theta plus E cos theta. That means twice of E cos theta along this PR, and this PR is from what? Positive to negative. That means in direction, what happened, the direction of electric field E is along this, and the direction of dipole moment is from minus q to plus q. So your electric field will be in the direction opposite to that of dipole moment. Got it? Yes. Let's see. Let me a little bit zoom out, okay, so that you will see the whole thing. Yes, so like that, resolving E plus and EB minus, as I have said, so this will be equal to, when you added up these two components, okay, for E cos, for E minus, E plus, or you can write E minus, because as the two are of same magnitude, so you better write it here like this, as magnitude of, or you can write like this. Instead, you can take it only in magnitude, okay, this one and this one. So but as these two are of same magnitude and along the same direction now means along PR, okay, so what happened, it will be equal to in this way. So twice QL is what? It is nothing but your dipole moment P vector, and your dipole moment P vector and E vector are opposite, so 1 minus should assign in that dipole moment. 1 minus should assign in the dipole moment, okay, so like that. Got it? So E vector is equal to 1 by 4 pi epsilon naught minus P vector divided by R square plus L square whole to the power 3 by 2, right? If R is very much greater than L, okay, as we did in the previous one, then what happened, your L square is very much small than R square, so that what happened, L square can be neglected when we compare with R square. So what happened, this will be R square whole to the power 3 by 2 only. So square and this square root, okay, will cancel, and R cube will be only there. So in this case also, your E equatorial, this will be equal to 1 by 4 pi epsilon naught minus P vector by R cube, right? And now here, see, in this case, what happened also, the direction are opposite to that of the electric dipole moment, electric field due to an electric dipole at each equatorial line will be in the direction opposite to that of electric dipole, and your magnitude of E is inversely proportional to the cube of the distance, okay, distance of the point of observation from the center of the middle point of the dipole, right? And moreover, in that, what happened, the previous one, that means along its axial line, this sign was not there, so it was plus, and there was a factor 2 there, right? Got it? So what happened, your E axial, that means electric dipole, when it is to find out electric field along its axial line, that is equal to 2 times of the electric field at its equatorial line. Got it? Yes, let's stop it here for today.